All right. Thank you, and thank you all for coming back, or coming, those of you who weren't here the first time. Ted, speak of Ted. Hi, Ted. Who won the game, Ted? Okay, very good. All right. Ted's suggestion was that I not ask for a break, but insist on a break at some point. So I will do that. I'll tell you the rough outline for today. And of course, who knows how long everything's going to take. It's entirely possible that I won't actually finish everything. But so first I'm going to do a brief recap of what happened last time and introduction to this time. Part 2 is Suslin Cardinals and the Solivay sequence, which is stuff that was planned for part 1, but I didn't get to it. Part 3 is the right definition of infinity-Borel codes. And then we're going to look at local infinity-Borel codes and strong infinity-Borel codes. The last part is on cone measures and their ultrapowers. And then at some point, I'm probably going to end with mentioning a couple target theorems for next week, probably 2 target theorems. So like I say, who knows how much I'll actually get through of that plan. The break is going to come either here or here. I don't know. We'll just see how long it takes to do things. So when I get to one of those points, I will order you all out of the room for 5 minutes. We will start again. Okay, so talk 1 was supposed to be accessible and gentle. We didn't really do any long proofs. Today is also supposed to be accessible. The proofs will get a little bit longer, but not dramatically bad. I'm saving all the really technical stuff for next week. So slightly longer proofs, but hopefully still everything is okay, accessible. So a quick review of just what we did last time. So lecture 1, what did we talk about? We talked about AD and ADR. We defined them, and uniformization, and gamma determinacy. And finally, after that, we defined AD plus, right? And we introduced the wage hierarchy and theta, hierarchy and theta, and Suslin sets, and infinity-Borel sets. One definition of them, not really the one we're going to use today. So I think those are all the things we introduced. We sort of talked through some fairly soft facts. AD implies ADR, which implies that there's no alpha-1 sequence of distinct reals. Right? ADR also implies, did I just say it backwards? I wrote the right thing. Okay, ADR. ADR implies uniformization, which implies DCR. Like that. Uniformization fails in models well, of, again, this statement here, Aleph1 not less than 2 to the Aleph 0 of the form L of S and R, where S is contained in L of R. It's not literally how I said it last time. I mean, last time I said it for S contained in the reals, but we also want to do it for S contained in the ordinals. It's the same argument as we did last time. So if I have one predicate that I add to L of R, uniformization is going to fail in that case. It's the same. What's that? Of L of R. Yeah, right. I just add one predicate to L of R, and still everything is going to be ordinal definable from a real and S in that case. So the same argument I did last time is okay in that case. Suslin sets can be uniformized. We did this last time. Suslin implies infinity Borel. And anything else? Oh, okay. What else did we say? The Suslin sets and the infinity Borel sets are initial segments of the wage hierarchy. Anything else I want to say about it? Which, assuming AD plus DCR, has height theta. Okay. All right, so those are all things we said last time. I also stated last time, I think I said this, and give it more emphasis this time, the Martin-Steele theorem, which says that assuming AD, the Suslin sets, I'm going to put in L of R first. Assuming AD, doesn't really matter if I assume it in L of R or not, but assuming AD, the following fact holds in L of R, Suslin sets are the sigma 2, 1 sets. All right, I think I did say that last time. The second one, I actually don't remember if I said it or not. Kekris's theorem, which says that L of R just always satisfies the statement that AD implies DCR. Right, whether AD implies DCR in general is open, but not in L of R. Okay. Now I stated the Moskva-Vakas coding lemma very quickly right at the end. I'm going to I stated a weak version of it last time, and I'm going to state a slightly better version, slightly more explicit version this time. I don't really want to state it exactly. It takes quite a bit of care to phrase it in just the right way, and I just want to give the version that's enough for what I want. So before I do that, I guess I'm going to define a couple of terms that we're going to use in this talk. So a pre-will ordering, right? So less than or equal to is a pre-will ordering. I mean, usually for us it's on the bare space, but I guess it could be on anything, right? If it is, reflexive, that's the one. Reflexive, transitive, and well-founded. It's essentially the order induced by a function into the ordinals, right? You have a function from any set into the ordinals, and you just ask whose value was bigger. That's equivalent to being a pre-will ordering. Theta, which we already defined, right? Theta by definition was the least ordinal. It's not a surjective image of the reals, but theta is also the supremum of the lengths of the pre-will orderings of the reals. What's that? Oh, well, we can say total, I guess. It's not really going to matter for what I'm doing. It can just be anything. I mean, it can be partial for all we care in this. I'm not really going to get into the definability that would make a difference. Right. So theta by definition is the least ordinal that's not a surjective image of the reals. This is also the sup of the lengths of the pre-will orderings of the reals. And I don't think that requires me to assume anything in particular, because pre-will ordering is essentially just the same thing as a function to the ordinals, right? So I think this is a theorem, but it's not a theorem. That it's more or less just a rephrasing of the definition. Okay, so with those two definitions in hand, I can give you my second version of the Moskva-Vakas coding lemma. So, coding lemma. And so it says, I mean, this is version 2 since I defined it already last time. But, so we're going to assume AD holds, and let, well, I'm going to say just less than star be a pre-will ordering of the Baire space of length gamma, right? So it's, well, it's induced by a function from this to surjection from this to gamma, basically. That's what it means, right? Every real is then going to have a rank according to this pre-will ordering, right? Basically, it's just its image under that associated function. Okay, so then, okay, so still I'm stating it in a weak form, and I'm sort of hiding some details, so I hope you'll accept this as a definition. But then there is a projective formula phi in less than or equal to as a parameter such that for all a contained in gamma, there exists an x, and A is the set of, nope, it's not the set of Y. It's the set of alpha less than gamma such that there exists a Y and phi yx hold and the less than star rank of Y is alpha. Okay? The point being that relative to my pre-will ordering, I've in effect made every subset of gamma projective in this pre-will ordering, right? So essentially, this gives me a way to associate subsets of gamma to reals, to code subsets of gamma by reals. Now, those of you who are familiar with the theorem may complain that I said projective and not sigma 1, 1. I'm just being very picky, right? The real formulation requires you to use not, well, first of all, it raises the issue of what sigma 1, 1 in a parameter means, right? You don't really want to be able to use the parameter positively and negatively, and really you don't want this parameter, but you want the two parameters equal and strictly less than, and a whole bunch of things that we don't really need to care about at the moment. So I'm saying projective. If I had just said sigma 1, 1, then under the naive interpretation of what sigma 1, 1 in the parameter means, it would have been fine. But I just didn't want to get into any of that. So we'll say projective in that thing, right? There's a projective formula, and it just is allowed to use that thing as a parameter. Okay. So for us, the importance of this theorem, there are three things we can get out of this. I mean, one I stated last time. So three consequences of the theorem. So one is, and again, this is all assuming AD, so the theorem is true. So assuming AD, right? And I guess for some of these I'll assume DCR, but maybe not. I guess, do I want to assume DCR? Sure, let's assume DCR. I'm going to mostly assume DCR anyway. So the first one is the one I said last time. So for all A contained in the Baire space, for all gamma less than the theta of L of A and R, the power set of gamma is contained in L of A and R. And moreover, there's an association, and there's a map in here that maps the reals onto the power set of gamma. Right? Just maps, I mean, X is my code for A, right? So it just sends X to A. Second consequence is that theta is a limit cardinal. Right? I can map the reals onto every ordinal less than theta, right? Onto the power set of every ordinal less than theta, right? So theta can't be a successor cardinal, right? Because if it were, I could map the reals onto theta, which is the definition of theta, that I can't do that. A third consequence that we want out of this, and the main one for what we're doing right now, is that the failure of less than theta determinacy is a sigma 2, 1 statement. Right? I mean, so by which I mean, if there were a game of this type that were not determined, then I could express that fact by saying there is some set of reals, and then I get to quantify over the reals after that. So I get to say, you know, it codes some free-will ordering. There is some game associated to that set of reals and some continuous function. And when I run my codes on all the different strategies, which I've coded, all the different strategies are really subsets of my gamma, right? That none of those things produce a winning strategy in the game, right? Okay. All right, so this is the important thing for us, is that if less than theta determinacy were to fail, then this is expressible as a sigma 2, 1 statement, right? There's a set of reals witnessing that fact. Okay, and then, I mean, maybe I shouldn't erase it. We're going to plug that into this fact, right? Right. If it failed in L of R, well, we've basically proved that what? That less than theta determinacy holds in L of R if AD does, right? Because if it failed, there would be a sigma 2, 1 witness to it failing, and that would be Suslin. And last time we proved, I mean, it would be Suslin and co-Suslin. Did I say the right thing? I mean, okay. Oh. Maybe I'm missing one more theorem that says I can actually reflect this down into delta 2, 1. Right, just the solid basis theorem says a sigma 2, 1 fact has a delta 2, 1 witness. And so then I can get this down into Suslin, co-Suslin. Maybe. All right. Maybe I need one more step to make that whole thing work. All right. The solid basis theorem. Which just says, well, in our case, it just says in L of R, we could probably. Yeah, that's what I'm trying to. I just hung myself up for a second. Yeah. Yeah. Right. 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 But I don't want to push it down here and use the fact that a Suslin example, there can't be a Suslin counterexample. That's right. Right. Yeah, yeah. Well, that's what I'm wondering, yeah. Can I push this down to get a Suslin, co-Suslin counterexample using this Holloway basis theorem then? I mean, there's a sigma 2, 1 fact. Yeah. Right. Right, yeah, right. That's right. Right. Okay. So maybe I need to. Yeah. So, but I think this saves it for the moment anyway. In L of R, sigma 2, 1 facts have delta 2, 1 witnesses. I don't think I needed that, but okay, maybe I don't need it. But I think this gets me down to Suslin, co-Suslin. Okay. Now, all right. While I'm at it, let me just recall what the definition was. I guess I have been talking about it, but what's that? Oh. Well, I'm going to write it later, but yeah. Yeah. Right. Right. That's what I mean, yeah. then I need the Solovay basis theorem to do it. Yeah, that's right. Okay. All right. So the conclusion, right? So putting all that together, assuming AD, well, I'll just say this, AD plus B equals L of R, right, implies less than theta determinacy. Okay. All right. Yeah, so Hugh, after the last talk, mentioned the following. So let me just write down what less than theta determinacy was again, right? So we had these games that looked like what? So less than theta determinacy said that for all gamma less than theta, right? For all continuous functions f going from gamma to omega to omega, where again gamma gets the discrete topology and this has the product topology. We have the game on gamma where the payoff set is f pre-image A like this. So 1 and 2 play elements of gamma. They're playing alpha 1, 0, alpha 1, alpha 2. They produce some object x in gamma to the omega, and then 1 wins if and only if f of x is in A. We apply f to the output of the game. So you might wonder why we have to do that, right? Why are we applying this f? Why don't we just start with a payoff set, which is a subset of gamma to the omega? And this is a standard argument to show that that's inconsistent. So let's just make that observation. Okay, so what should I say? So it's not true. Right, let me say it this way. There exists an A contained in omega 1 to the omega such that the game on omega 1 with payoff set A is not determined. Yeah? Okay, so we can't just play the games directly on omega 1 and have a payoff set in omega 1, right? The amusing thing about this fact is the proof doesn't actually produce a specific A for us, right? So first of all, we know that if G omega A is determined, that's just AD, right? For all A contained in omega to omega, then there's no injection from omega 1 into the reals. Okay, but now we can contradict that with a game on omega 1. We have the following game in which player 1 just plays an ordinal in omega 1, so that's in omega 1. And now player 1 doesn't do anything else from now on, and player 2 just has to play a code for that ordinal, which is a countable ordinal. So it just plays, you know, x0, x1, x2, and so on. Right? And so now 2 wins if and only if x codes alpha. I mean, if you want, x could code a well-ordering of omega of order type alpha or something, right? But now nobody can win this game, right? Certainly 1 can't have a winning strategy because that would just be an alpha for which there's no code and there's no such thing. But 2 also can't have a winning strategy because that would give me an injection from omega 1 into the reals, right? Because that would, for every alpha, I'd be playing a real, a different real, okay? So, okay. And the amusing thing is it doesn't produce a specific game that's not determined, right? Right? If all the games of this type are not determined, then there's a game of that type that's not determined, right? It is actually consistent that all the definable games are determined. It's the theorem of Hughes, right? So there isn't a theorem of the type that says this game of this type is not determined, right? It's just, you know, globally there has to be one that's not. Okay. Taking a lot of time. All right. Very good. So, make sure I've said what I want to say. Good. All right. All right, so questions. And I kind of forget if I said these things or not last time, but we should just emphasize it. So the big question, right, is does AD imply AD plus, right? So that is open. The answer is yes in L of R, right? we've basically seen that. We've seen it for less the ordinal determinacy, and Kekris gives it to us for DCR. We haven't quite seen it yet for infinity Borel, all sets of infinity Borel, but we will do that. You could also ask things like, do the parts imply one another? You could ask, does AD plus any two parts of AD plus imply the third part of AD plus? And those are all open as far as I know, right? Some parts of AD plus are actually consequences of choice, so they're not going to imply the other parts, right? I mean, DCR and all sets being infinity Borel, right? So AC implies DCR plus all sets, whatever, plus power set of the bare space is contained in infinity Borel. So certainly those things aren't going to imply the other parts of AD plus, right? Okay, but yeah, AD plus, any two parts of AD plus implying the third, right? That's an open question in all of those cases. In fact, it's open whether ADR implies AD plus. Does ADR imply AD plus? Well, now we've seen already that it does imply DCR. All right, so one part is down. In fact, we talked about it last time, and it is sort of one of the target theorems for this series, but I don't know if we're going to get to it. It does imply that all sets of reals are infinity Borel. So those two parts are okay. So in fact, you could rephrase this. This is the part that's open is just, does ADR imply less than theta determinacy? Right. Even this part is known if DC holds. Yes, if DC holds. And I'm going to talk about that a little more in a second. Okay, but without DC, this is still an open question. Okay. In fact, okay, well, I'm gonna sort of rephrase these two things, right? So, okay. Yeah. Okay, so just rephrasing what I just said. So it's a theorem that AD plus uniformization implies that all sets are infinity Borel. Right? And it's a theorem that AD plus DC plus uniformization implies that. What did I do? Okay. That's what, okay. Anyway, I'll fix it. I skipped a bunch of stuff I meant to say. Was this making sense? Okay. Anyway, all right. AD plus DC plus uniformization implies that all sets are Suslin. Okay. This is, these are due to Hugh, right? So this is Wooden. They're both due to Hugh. But this one uses some work of Howard Becker. So, okay. So putting this all together, we have the following sort of theorem that compares everything. So I'm just going to write it this way. So 1 if and only if 2, and I hope this isn't confusing to write it this way. 2 implies 3, implies 4, right? And also DC and 4 implies 1. Right? So DC gets us back to 1. So again, this is due to Hugh. So 1 is, actually I stated it not in the order you'd expect to, but somewhere. AD, oh maybe I did. AD plus every set of reals is Suslin. And AD plus everything is Suslin. The third one is ADR. And the last one is AD plus uniformization. Okay. Now among these, let's see, this one is easy, so we've done it, right? This is the one that's stated right here that uses Howard's work. This one is certainly easy. Well, okay, this one is easy if I said the thing that I skipped that I meant to say before, so we will sort of recap what I skipped over. And what else? What about this one here? We will say it. Have I said it? Have I said anything that implies? No, but I mean, okay. This one, in my original conception of how these lectures were going to go, I was going to prove 1 implies 3 on the last day of this. We'll see how this goes. This may or may not happen. Okay, so, okay. Very good. Yeah, the thing I skipped was the definition of AD+. I wanted to remind you what that was. I guess, let me just say it again. I'll erase this. Okay, so, again. So, AD+, we stated it as 3 parts, right? There's DCR, and there is, every set of reals is infinity Borel, and finally less than theta determinacy. Okay, and what I wanted to recap are the 2 things that we said at the end last time. So one was all 3 follow from AD plus all sets Suslin. As does ADR. Right, ADR follows from that also. Okay. And for all 3, okay, so I'm going to state this somewhat awkwardly. For all 3 parts, right, if, what should I say? If A is a set of reals and L of A and R is contained in some M where A satisfies this part, whichever part it is. So I'm just going to write the part somewhat awkwardly, but whatever part we're talking about. That word is satisfies. Satisfies the part in M, then it does also in L of A and R. So all of these things reflect down. If there's a larger model containing the reals that satisfies one of these things, then L of A and R itself also does. And this one is not true for ADR, so this is unlike ADR. Right, so the parts of AD plus reflect down to any model that contains the reals and the set. Right? ADR itself doesn't. And everything follows from all sets being Suslin. Okay. Okay. Got 17 handwritten pages, and I've done 3 of them for 35 minutes, so we'll see how this goes. What's that? 14, oh yeah, only 14 to go, yeah. So you can all count down with me, yeah. Okay, so, all right. Yes? Yes. The part, right? So the part, yes, for all 3 parts. Yeah, and then this is somewhat of an awkward formulation, but okay. Okay. Well, we'll just take it as it comes. I'm not going to skip anything. Okay. I should say. So now, personally, I revealed one of my dreams in the first lecture. Another one of my dreams is to prove that AD doesn't imply AD plus by forcing to add a new set of reals on top of the wage hierarchy and not adding any sets of ordinals and preserving AD while you do it. Nothing that I know of actually says that that's impossible to do, although there's lots of information we're going to see that says what the starting model would have to look like. You'd have to start with a model of ADR and theta regular and a bunch of other things, but you know, that's one hope for separating AD and AD plus. One could also hope that they're the same. Okay. So I want to state, well, eventually I'm going to state some consistency results, but one more theorem of Hughes before that. Okay, so I'm just going to define the following point class. So gamma plus is going to be the set of subsets of the Baire space for which L of A and R satisfies AD plus. So that's just going to be gamma plus. It's an initial segment of the wage hierarchy. And I guess it's non-empty if AD holds. Okay. So here's a theorem of Wooden's that just shows you that the consistency of AD and not AD plus has some significant consistency strength. So if we assume any model, if you take any model of AD plus DCR, this model here, L of the point class of things that satisfy AD plus itself satisfies AD plus. So if I collect together all the individual sets that give me models of AD plus, the model that contains them all satisfies AD plus. And furthermore, if it's not everything, right, so in particular if AD plus failed, then when we cut off at that model, we get a model of not only, well, we get a model of DC plus ADR. Okay, so there's a model of ADR waiting for us at an initial segment of a model of AD and not AD plus. And this actually, I'm gonna mention this theorem later on, and so I wanted to give it a name so I could refer to it. So I'm gonna call this the gamma plus theorem, unless anybody has a better name for it. But I made up the terminology gamma plus, so this is an especially bad name for this theorem, but I will come back to this. I mean, later on we will see something that sort of explains the DC part of this. Okay, but for the moment it just says that, well, it just says this. If I happen to have a model of AD and not AD plus, that's essentially what this is saying, right? Then there's some wage initial segment that satisfies the stronger axiom, ADR, there. What's that? Well, yeah, right. So that's, I guess, what you know. I mean, you know that theta has uncountable cofinality, and that's what it means, right? Yeah. Okay. All right. Okay. But still using this. Okay. So here's the standard consistency result for AD plus, again, Hugh, right? So this is the derived model theorem. It's one version of the derived model theorem. Maybe this is the old derived model theorem. I'm not even sure there are only two versions anymore, but okay. So if we let delta be a limit of Wooden cardinals, and let gamma be generic for collapsing everything below delta to be countable, right? And we're going to let R star, it's going to be the union of the reals that appeared in intermediate models along the way. Fine, I guess I'll do that. So this is just the R's of V of G restricted to lambda, where lambda is less than delta. Right, delta in this situation could have countable cofinality, so there could be reals that are added by the whole forcing that are not added by some initial segment. We don't want them. We're going to let gamma, in this case, be, well, it's going to be the set of subsets of R star such that A is definable using sets that were added, well, definable from elements of V or from reals that showed up along the way and which are in this gamma plus. All right, so L of A and R satisfy AD plus. Okay. Then this model, L of gamma and R, satisfies AD plus. Okay, so this model here is called the derived model. Okay, so this is our, well, it's our standard way of producing models of AD plus. And in some sense, it's the only way of producing models of AD plus. Because the derived model theorem has a reverse. What's that? What is R star? Oh, R star, yeah. L of gamma and R star. Yeah, that's right. We don't care about the reals that were added by the whole thing. So the derived model has a reverse. I think it has been proved in every case, right? So if we assume that our ground model satisfies AD and DCR, then when we compute our gamma star for us, right, L of gamma plus R as defined for us is the derived model of some inner model. Some inner model which we may not see, it may not exist in L of gamma and R itself, but some inner model which exists in some forcing extension. Okay, so, all right. So the models of AD plus are exactly the derived models then. Yeah. Is that, yeah, okay. I mean, I thought this was done in every case, but is it not? Right. So the missing case is this right? Is it still missing then? You're saying there's one case where it's not established. So it is. That's what I thought. Okay. Yeah. Right. Okay. Yeah. Right. That's what I thought. Okay. That's right. So yeah. What the case was? What ADR plus theta is? Right. Was the last case to fall. Right. Okay. Right. Okay. Very good. Okay. There's one more theorem in this set that I wanted to mention. Also due to Hugh, right, which is that, okay, so assuming AD plus DCR, am I saying the right thing? No, just AD, I guess. Sounds okay. Assuming AD plus is equivalent to the statement that every sigma 2, 1 statement, every true one, not the false ones, has a Suslin co-Suslin witness. Okay, now I think one of these directions we have seen. I guess if every true sigma 2, 1 statement has a Suslin co-Suslin witness, well, we've almost seen it, not quite for infinity Borel, right? I guess this is the argument I thought I was doing before when I said we could reflect a failure of ordinal determinacy. I mean, failure of ordinal determinacy would be a sigma 2, 1 sentence, which we could reflect into Suslin co-Suslin, then it wouldn't, in fact, be true. I'm sorry? Which is sorry. If the sigma 2, 1 statement is true, so a sigma 2, 1 statement says there exists a set of reals such that blah, 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 quantifying over the reals, then I can assume that that set of reals, the existent set of reals, is a Suslin co-Suslin set, and I can quantify over the rest, right? Okay, and then this fact was, especially useful for me when I was starting out as a grad student, because this was the fact that made AD plus the right context in which to do Pmax, right? This is what what allowed PMAX to work over models of 80 plus, right? The fact that you could reflect, right? You wanted to show that A-iterable models existed, and if there was a bad A, then there was a co-Suslin one, and there couldn't be such a thing. So, okay, so this. Right. 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 Yeah, that's right. So that's a good way to say it. Yeah. So the solid basis theorem is in fact. Right. This is a generalization of that, just for all models of 80 plus. Okay. Well, let's see. I guess I lied to you about when I was going to take the break because it's halfway now. So let me insist on the 5-minute break now, and I will start again. So I'm still going to define Suslin cardinals and the Solovay sequence. I mean, we'll see. That's going to happen next. It'll happen starting in exactly 5 minutes. So. Yeah. But we're breaking. But you can still ask a question. I'm going to turn the mic off and answer your question. Yeah. We still have about 30 seconds on our break. Okay. Okay. All right, so we'll finally define the Suslin cardinals and the Solovay sequence. So let's do that. So Suslin cardinals. Okay, so a cardinal kappa is Suslin if there exists an A contained, yep, good, in the Baire space, which is kappa Suslin, but not gamma Suslin for any gamma less than kappa, right? And we can remember kappa Suslin just meant that A is the projection of T for some T on omega cross kappa. Okay. Okay. I have the following theorem, which I assume is just folklore. And the question is, do I want to assume AD, which I didn't write it there, but I think I do. Assuming AD. Yeah? Is it okay? Assuming AD, let's just say it this way. Every set is Suslin. Power set omega omega is contained in the Suslin sets if and only if the Suslin cardinals are cofinal in theta. One of the two directions is significantly easier than the other, right? If every set is Suslin, well, if you fix a kappa, the Moskowakis coding lemma tells you that you can map the reals onto the kappa Suslin sets, and so not every set of reals can be kappa Suslin for one fixed kappa, so the Suslin cardinals have to be cofinal in theta. In that case, if all the sets are Suslin, then the kappas that witness that have to be going up to theta, and they have to be cofinal in theta. The other direction, well, I was surprised by how much work it takes to do. I mean, the thing is, we know that Suslin representations really don't have to be local, right? You can have a model of set theory that has a set of reals that's not Suslin in that set, but is Suslin in some larger set, in some larger model, right? So a set of reals can be Suslin without any way of producing the witness to its being Suslin. So we know that the kappa that witnesses that a set is Suslin doesn't have to be close, for instance, to the wage rank of kappa or anything, right? But nonetheless, right? Yeah, oh. Yeah, so maybe I meant to write DCR too. Yeah, the wage order is just, yeah. I agree that anytime we want to talk about the wage hierarchy, it just gets too weird if we don't write DCR. Yeah, so, yeah, let's do that. That's also true, yeah. But I mean, cofinal in theta just is going to be, yeah. Once we start talking about theta, we want to have DCR around. We want the wage hierarchy to be well founded up and actually have order type theta. Okay. All right. Now to Theorem of Steel and Wooden, I believe independently. That AD, maybe I should start writing DCR all the time after this. AD, I don't know, implies that the set of Suslin cardinals is closed below its supremum. Right, so it's a closed set except that if its sup happens to be below theta, I mean, if the soup is below closed below its supremum, right? If the soup is, what I mean is, if the soup is less than theta, right? It's closed below its supremum. Its soup may be theta. I mean, the Suslin cardinals are all less than theta, right? We did say this last time, right? If I said it's Suslin for something below theta. Okay. All right. So AD implies that the Suslin cardinals are closed, although for all we know, it's consistent with AD that the soup of the Suslin cardinals is some ordinal below theta, which is not a Suslin cardinal itself. However, Hugh showed, I'm going to write DCR. Probably DCR belongs on this one too. Implies that the set of Suslin cardinals is closed. That is something that I was hoping to outline a proof of. Below theta, yeah. Right, of course. It can't be. That's an equivalence, right? That's the last thing, yeah. So, but the equivalence is, I mean, this is something that I was thinking that I could outline a proof of. Right, the equivalence, the other direction of the equivalence is, well, it's like the reverse direction of the derived model theorem, but it's going to be harder, and so, yeah, right. There's a plus there, it's just in the wrong place, yeah, that's right. I'm not sure if I need DCR or not, but I can. Oh, DCR is part of it. Yeah, okay, so definitely don't need it. There we go. Nice. Lovely, okay. All right, so so the following is sort of an exercise in propositional logic, but we will say it. So this difference characterizes the difference between AD and AD plus. So assuming AD plus DCR, well, the failure of AD plus is equivalent to the conjunction of the supremum of the Suslin cardinals is below theta and not a Suslin cardinal. Okay. And I think one of these two directions we've seen, right? Well, in fact, let's see. Like I say, it's an exercise in propositional logic, but the backwards direction is the previous theorem, right? Right. In the forward direction, well, we have two cases, right? If the Suslin cardinals are cofinal, in theta, well, that implies that all sets are Suslin, right? Which implies AD plus, since we're assuming AD. Right? That's one of our two cases. The other case is the hard case, right? If the soup is, right? If the soup is less than theta but Suslin, that's the case where we're getting AD plus. But I mean, I'm not saying anything about how you get that. It's similar to the reverse direction of the derived model theorem. Okay. All right. So those are the basics of, I mean, that's basically what the Suslin cardinals are. We're going to connect these to the Soloway sequence. All right. Okay, so. All right, so Soloway sequence is, well, it's a unique sequence such that, well, here we go. So it's, well, I'm going to write down the sequence. So the sequence looks like theta alpha, alpha less than something, less than or equal to some beta, less than or equal to, such that theta 0 is the least ordinal, which is not the surjective image of the reals under an OD function, an ordinal definable function, right? If I left off the letters OD, then that's just the definition of theta. So we're restricting the class of functions we're allowed to use to the OD ones, right? So this is necessarily less than or equal to theta, because we just shrunk the set of functions. It's unique. It's continuous, so that tells me what happens at limits. I'm just going to take soups at limits. For all alpha such that alpha plus 1 is less than or equal to beta, theta alpha plus 1 is, at least I'm repeating the same definition, but I get to throw in a set of wage rank theta alpha as a parameter. So it's the least ordinal, which is not a surjective image of the reals under an ODA function for any A contained in the bare space of wage rank theta alpha. Okay, so one thing to keep in mind, of course, is that the sets that are all of wage rank theta alpha, well, if I took any one of them as my one fixed parameter, I would get the same soup. I can define the same set of surjections in an OD way from any set of reals of wage rank theta alpha, right? So here I said, well, you can take anything of wage rank alpha, but I decided to fix one first and say, for that one, I get the soup of all the ordinals that are not the image of the reals under ODA functions for that A. It's the same definition, right? Because all of those sets are definable from one another with a real. Okay. All right. Oh, the last part is theta beta equals theta. The sequence ends when you hit theta, right? So theta beta is the real theta. That's supposed to look like a thin lowercase theta, and that's an uppercase theta. That's the one at the end of the sequence, right? So we keep increasing until we hit theta. So, okay, so our first observation about this is that theta 0, right? So number 1 is in L of R, right? Theta 0 is theta, right? So beta is 0 in that case, right? Theta, thank you, yeah. Theta 0 is never 0, as it turns out. Yes, yeah, theta 0 is theta. Right? Every function is, well, everything is ordinal definable from a real, but you can just throw in the reals as extra parameters, and I mean, you're allowed to have the reals in the domain of your function. That's right, yeah, because, yeah, that's, if you, no, it's not that, it's just that you're allowed to put, the reals are allowed to be in the domain of your function, right? So you can pull the reals out of your parameters of your definition and then just plug them in when you apply the function. Okay. All right. If I assume AD, let me just look at what I'm assuming. Assuming AD plus DCR, that's just to get the wage hierarchy well-founded, plus uniform. Well, a definition, I mean, the context is certainly AD plus DCR. I mean, yeah. I mean, it's a definition, right? So you can, I mean, yes, we intend to use it under AD plus DCR, but you can make the definition regardless of what holds, right? I mean, yeah, well, yeah, we're going to apply it when the wage hierarchy is well-founded. Yeah. If we assume that AD plus DCR plus uniformization, then beta is a limit ordinal, right? Right, so in particular, if ADR holds, the Solovay sequence has to have limit length, right? Because otherwise what? If it had successor length, right, what's happening? Then, I stopped at theta alpha plus 1, and here's theta alpha. I have some set of wage rank theta alpha there, right? Well, if I use in L of A and R now, right? What, I've got surjections onto, well, I have pre-will orderings of all the lengths up to theta alpha plus 1, which also means that every set of reals is going to be, because the wage ranks of those pre-will orderings have to soup up to theta alpha plus 1. So every set of reals is going to have to be ordinal definable from A and a real, right? And so uniformization, our standard uniformization argument is going to fail in that case, right? So if the Solovay sequence has non-limit length, and I could have just put this 0, the same argument would have worked there. Right? If I have non-limit length, then uniformization fails. So in the case where ADR holds, Solovay sequence is going to have limit length. It's almost an equivalence. I mean, it should be an equivalence, and we're all rooting for it to be an equivalence. So the almost equivalence says, well, all right, so this is note 3, I guess, right? If I assume less than theta determinacy, I'm going to turn that into a letter D, determinacy plus DCR holds, it's in one sentence, right? Remember, less than theta determinacy implies AD, right? And the Solovay sequence has limit length. Right? Then ADR holds. All right, so in particular, AD plus, under AD plus, right, whether or not ADR holds is just the question of whether the Solovay sequence has limit length or not, right? We'd like that to be just assuming AD, but at the moment it's just assuming AD plus. Okay, right, so the question is, does AD plus DCR suffice for this? Okay. Now, okay, the next thing is sort of a rephrasing of 3, but it's the rephrasing that Steve used in his talk, so I thought I would just say it. Okay. All right, so note 4 follows from note 3, basically, but so whatever. On this one. Right. Right, so you get, okay. So you're saying this does give you do get uniformization out of that, but not necessarily, not known. That's not very good notation there, but I'll just say yes for uniformization, but not for ADR. Okay. All right, so item 4 is basically a rephrasing of item 3. It just says, assuming ADR now, AD plus now, again, it's another exercise in propositional logic. ADR fails, right, if and only if there exists an S contained in the ordinals such that L of P of R is L of S and R. Okay? And again, let's see. This direction just comes from the failure of uniformization, right? This model doesn't satisfy uniformization, so if this is happening, then we don't have ADR. And the other direction is kind of a rephrasing of 3 here. Okay. If we don't have ADR, we have limit length, right? So there's a top, so we look like this, right? We're at a successor length. We have an ordinal set of reals of this length here, AD plus holds, so that set is infinity Borel. Right, so it has an infinity Borel code, and there we are L of S and R then, in that case. Did I skip something? Well, no, yeah, okay. That's true. So do I have an easy argument of that type then? Let's see. I'm wondering, can I make it work from what I want to say right now? No, so maybe it's harder. Maybe I have to, there's a harder argument to get the S than what I just said. Yeah, that's right. I can't do it in a soft way. All right, sorry. That's true. I can get the A, but yeah, that's right. That's right, no, yeah, just the fact that it's just 3 is not quite right. Okay. All right. All right. So item 5 here is due to Solove, and the rest of it's due to Hugh. All right. So Solove, which says, assuming ADR, right? ADR implies that the model L of P of R satisfies DC if and only if the cofinality of beta, this beta, is uncountable. It's greater than omega, right? Even only if the length of the Solove sequence has uncountable cofinality. And of course, he didn't call it the Solove sequence himself, but this is where the Solove sequence comes from, this paper. Right? Okay, so certainly, right, I mean, we can think this through for a second. Certainly if beta has countable cofinality, DC is not going to hold, right? We're not going to be able to pick a sequence of reals, an omega sequence of reals whose wage ranks soup up to theta. Because if we did, we could just sew them together and get a set of reals whose wage rank was bigger than all of them, which is what theta says there isn't, right? So certainly if theta has cofinality omega, DC has to fail, but that's the only way the DC can fail in this case. Okay, so let's see. All right, so I guess I'm going to finish with just one sort of comparison of the Suslin cardinals with the Solove sequence. All right, we have 2 different sequences below theta, and at least in the 80 plus context, they're both closed, and it's natural to ask how they compare to one another. Okay, so let's just close with this picture, right? We started with the wage, so let's just assume, in fact, I'm just going to assume 80 plus for this picture. We have the wage hierarchy, which again is giving us these classes which are dual and self-dual, like this. We have the Solove sequence, right? So theta is being chopped off at, we have theta 0, theta 1, eventually some theta alpha plus 1, etc. Right? We get a bunch of models of determinacy along the way. If I let gamma alpha be the set of A contained in omega to the omega such that the wage rank of alpha is less than theta alpha, right? Well, I get a model of, well, any model containing the reals is a model of AD plus. So I get the following models. I could look at L of gamma alpha and R, right? Or I could just look at HOD, where I allow myself the parameters in gamma alpha. Okay. By the definition of the Solove sequence, I'm not reaching above gamma alpha, right? This is, right? So this model intersect power set of omega to omega is gamma alpha, right? But this model is contained in that model, so that's also true for this model. Okay. Okay. Apparently these are unnatural models of determinacy. Now at the successor steps, however, right, if I'm cut off here at theta alpha plus 1, right, not all of my sets are Suslin, right? So in a particular model that looks like this, that looks like L of, now which way did I say it? Gamma plus 1 R, right? This one satisfies the failure of uniformization, right? So the Suslin sets of that model die out at some point. After some point, I'm not seeing Suslin representations anymore for those sets. In fact, they die out at, right, the largest Suslin cardinal here. Again, this is, right, the largest Suslin cardinal in this model is the delta 2, 1 of A, where A has wage rank theta alpha in this case. Okay. All right, so my Suslin representations die, but they pick up at the next. Is this not the right thing? Yes. Well, okay. I mean, I'm assuming the hierarchy continues past there. So I didn't finish my assumptions about the situation. I mean, I'm assuming that alpha plus 1 is not beta. I didn't say it yet, though. Yeah. So, yeah. So, however, right, if the sequence continues here, right, so if there's another theta on top, then all of these sets are going to be Suslin. They're going to have Suslin representations in the next level, right? Okay. Yeah. Okay, I mean, all right. Well, I think the following is still true, that the sets that are, okay, let me just say it this way, right? Yeah. I see. Right. Right. Okay. All right. I mean, the main point I want to make is the relationship between the Suslin cardinals and the Solovay sequence. And so what I believe to be the case, you can tell me, is that the theta alphas below, and assuming 80 plus, the theta alphas are themselves Suslin. Right? So in this case, each theta alpha below theta is Suslin. And, well, I thought it was true. It sounds like you're telling me it's not true. I thought that in the gap between each successive pair of thetas, there were many Suslin cardinals, but this is not true? I thought in the gaps between thetas, there were many Suslin cardinals, assuming 80 plus. Except in that. I see, okay. Right. I see. Okay. Okay, so maybe it's more complicated than I was saying. I mean, it's all right. Okay, so where am I? I've got. All right. I've got 10 minutes. I wanted to start talking about the infinity Borel sets. I'm not sure it really makes sense to do it for 9 minutes. Oh, this is where the first break was supposed to happen. Yeah, I think that's what I will end early, and we will pick it up next week with the infinity Borel sets. I think that's the best thing to do, because I think Noah's starting right away after this. Isn't that right? Yeah, so the next talk is soon anyway. Okay, I'll stop here. Thank you.